All right, so today is our last major sort of technical lecture. Moving forward here, the lecture L, I think, this Canvas the L, I think, was actually due today, but we normally would slice in one other kind of round out lecture that didn't have a lot of new technical content. I do spend a lot of time in lecture L beating up on companies like Samsung. So if you like to take a look at that, it's a PowerPoint that is online you can download, but we're probably not going to hit lecture L today. We're pretty much going to focus all on lecture K2 content. No more homeworks, although I did extend some homework availability. No more labs, although there's some, I think, availability running out here. So really the focus here is on that final project. Your final project, I've been talking to a lot of people about their projects and how things are going. You don't have to get too ambitious, like something on the scope of homework J2, something like that is kind of what we're looking for, a model that has a little bit of complexity, has a few input models that are definitely fixed to real world data that allows you to make an interesting conclusion that you couldn't have made without the simulation. So should the company get rid of this or get rid of that? Should they add this thing? Should they change the order of these things? And how do we have sort of some good evidence behind that? That might involve measuring an absolute performance estimate or increase or decrease. So we know that if they make this change, they'll make so many more dollars per hour. And if that's the case, you should probably also compare that with cost. And so we estimate that this change will cost this much per hour to make. And so do those things balance out? It's totally okay if you end up just saying that the intervention we came up with doesn't work, like it's not worth it, or it is no different than the current model. That is not a failure. So remember, a positive result that's statistically detecting a difference from the baseline, that's great, but sometimes there aren't positive results. Sometimes it's just bad ideas. The positive result could be a negative in terms of valence. It could be a poor idea. Like you might be, does differ from baseline, but it's actually a lot worse than baseline. And that is totally okay. So, or you might find that that there's a lot of uncertainty because of maybe you need more data for your input models to really nail down certain parameters. And if those parameters were kind of, shifted up or down from the ones you estimated, then you might get very different results, in which case your conclusion might be that there could be some very different conclusions we could make, but we're going to need to invest in more data collection in a later phase of this project, which you wouldn't do, but you'd be sort of suggesting what's the next action to take. So, there's a lot of different ways that your conclusions can come out. A successful project is not necessarily only going to be ones that show that you've come up with an intervention that works. Your goal in this class is not to come up with ways to optimize Starbucks. Your goal in this class is to come up with ways to use simulation modeling to make more compelling arguments. So that's really what I want you to practice on here. There's a question in the chat. If we weren't able to fit a distribution correctly during the input modeling report, do we need to resubmit data before the final? Great question. But no, the input modeling report doesn't need to be connected to your final project report. The input modeling report was really just meant to be a proposal and to show me that you've built some momentum on working on the system. I'm not going to go back and look at the input modeling report and see if things match up or see if things have been fixed there. But you need to make sure that whatever arguments you're making in the final report are convincing. And so you might if you need to make an argument like, the inputs to this, the interarrival times are exponentially distributed at the mean of 5 minutes or something like that. If that ends up being a very important parameter in your system that you really got to get right, then that's something that maybe you're going to want to show that input modeling. So it's kind of up to you as to how to make the arguments convincing. You can take a look at the rubric and what's kind of expected of it, but I'm not necessarily expecting you to give me every single input model like in the appendix or something like that. You could, but just make sure you refer to them. Don't put anything in your appendix that you don't refer to. But the goal here is, again, to make that argument. And some things, like, it's going to be very believable, the input model that you pick. But other things that are a little bit weirder, like if your inter-arrival times are exponential one time a day and Weibull another time a day, and log normal another time a day, then you start sort of saying, well, maybe I need to understand more what's going on in the system here, and need to justify to the reader that I understood my system and I didn't miss some structural problem. So just those sorts of things. I hope that answers the question. Any other questions? Project, by the way, so this will be the last lecture of this week. Go over the Thanksgiving holiday, and then next week we come back. Tuesday will be a final exam review lecture, and then Wednesday will be when the final report stuff is all due, final report and final presentations uploaded to Canvas, and then Thursday will be that stage 1 of the exam. That's the schedule going forward. So any questions about that? Seems on track. This, for the final exam resources, because stage 1 and stage 2 are administered online, but because stage 1 uses that lockdown browser, we do have a similar sort of lockdown browser compliance test. And if some of you have taken it already, make sure to take that sometime well before the final, and that will unlock the final exam module with a whole bunch of resources, sample exams, other sort of practice materials, and so on, including the ICA that'll be due before that Tuesday. And so that ICA is another one of these big ICAs that samples from previous ICAs. It's worth extra points. You can take them multiple times. It'll take the highest grade. So so come with your questions to, that when on Tuesday for that final exam review lecture, I can just, plug in my tablet and work problems, or we can go through the lecture slides that I've got that are kind of like the greatest hits from the previous lectures that might be on it, or whatever we like. It's really up to you guys. Just come with your questions online or in person. All right, so any questions? Pretty clear? Okay. All right. Okay, so we have, this is, we've been closing out the course with a discussion of variance reduction techniques. So by now in the course, we know how to simulate, we know how to model and simulate. And now we're getting to the point where we've built our simulation and we want to make sure that we can get as much bang for our buck out. So to get as much statistical power for as few statistical replications as we can. So reducing the amount of time we need to actually do simulations and do important things. And then last time we started out, and so that basically all I'm saying here is instead of focusing on increasing replications, we're coming up with clever ways, or hopefully clever ways, to decrease the variance that comes out of our simulations. And so last time we introduced common random numbers, which we've talked about a couple of times this semester, even if we didn't say specifically about that, where the whole role of common random numbers, which I'll just sort of step through here, maybe just hit the greatest hits here of this selection here, is instead of running independent replications in our 2 different conditions, so say we've got a baseline and an intervention case, then instead, where this independent case would be, we run different customers or different order schedules or whatever, the different inputs into both conditions. Instead, we pair them up and we basically run the same order sequence into both conditions kind of in parallel, and then we compare how they do for that input sequence. And we do that for multiple input sequences. And how do we do that? We do that by using the same random number seed. And so this is like 10 random number seeds, where each random number seed goes into both the as-is case and the intervention case. And then we look at the output for that random number seed, and that becomes a single data point. Then we use a new random number seed into both, and we look at the output. By the output, I mean we look at like the difference between them, and that becomes a single data point. And that's kind of summarized here, where I've got 9 random number seeds. So this is, 10 random number seeds. So this is like, imagine running 10 replications, and replication 0 has a certain random number seed, and that random number seed goes into both the as-is case and the intervention. We look at the performance difference, and the difference becomes the data point for that replication. And we do that 10 times. And that gives us 10 data points that we can then ask, are those data points significantly different from 0? And then we can use a paired t-test to test for that. So the null hypothesis is that there's 0 difference between these. And we detect a significant difference away from zero, we've detected that one system is significantly different from the other. And with that, you can go from an independent sampling where the difference in performance between all of your two models is really different, to the paired difference here, where you end up finding that these models, like your two different models, tend to kind of move with each other. And so this really shows you that most of the variance in performance you see here in the independent sampling case is just due to bad luck. So it's due that one of these happened to get a much harder order schedule on the input than the other one. And so what we do is we say, okay, we'll give all of them the same inputs. So we kind of make it a fair game. And then we sort of watch that playing that same fair game with the same challenges, how well do you do? And you can see these little pairs move around, and that reflects that this might have been a very difficult input stream, and this might have been a very easy input stream. But once we kind of factor all that out, all we really care about is the differences. We don't care about the absolute position here. And now we can see that there's consistent patterns. One model is consistently performing above the other model. And the difference between the models, there's not that big of an effect size. That is so small that it's totally washed out in the independent sampling, but we pick it up here. So if we were to pick up this small of an effect size with the independent sampling, we might not need 100 replications, we might need 1,000,000. Because remember, you can always pick up a small effect size if you sample more and more and more. But we may not have the computational budget to do 1,000,000 replications. So by cleverly coupling the inputs, we can now pick up a tiny effect size with only 100 replications. So that's kind of the point of common random numbers. Okay, and we can do that in ARENA by going into the seeds element, and you can go in and you can add a seed. You can name your own seeds, or you can use 10 for the default seed. And if you select initialize common down here, then what that does is it forces every replication to use a consistent numbering scheme, in which I think it's 100,000 more than the previous random number seed. And in that way, if you've got a bunch of different models stored in different DOE files, if this is set up the same way, you run model 1, you close ARENA, you run model 2 will have exactly the same seeds going into its replications, even though it's a different model. And so this just sort of forces it so that normally what would happen is after you run replication 1, replication 2 just kind of picks up with the random number seed where it left off with replication 1. And so there's no consistency across replications across different models. This forces it so that you've got the same random number seeds starting replication 1 across all your models, replication 2 across all your models, and so on. So then you can take the output of these things, dump it into the output analyzer or jump, run a paired t-test, and you're good. And that's all I'm kind of saying here. And then so if you do your own custom stream, anywhere where you put a random number expression, you just add another argument to the end of the normal arguments where you put that custom stream. But if you don't do that, it just defaults to 10. And so back here, if you put 10 there and say common, it'll just change the default random number stream to have this common random numbers property where it uses this seed in this consistent pattern. So that's common random numbers. The downsides of it is that sometimes it doesn't work. So you really depend upon your model to be similar enough so that if you did run the same customer stream in, if it was difficult for one model, it will be difficult for the other. But if you fundamentally change your model so that one model is really built and optimized for bursty traffic, and the other model is really built for more consistent traffic, then if you make the traffic more bursty, it's going to be really bad for the consistent traffic, but it's going to be really good for the other one. So if you fundamentally change the structure of your system, common random numbers might not work because you're not kind of shifting them in the same direction. And so you're actually going to increase variance by using this. And so typically before you use common random numbers, you can run a little pilot where I'm going to run 10 replications of each and then compare the variance. And if I get if I take the variance out of model 1, the variance out of model 2, and then I look at the variance and the differences, if the variance and the differences is less than the sum of the variances of the two models, then common random numbers probably is a good idea to go forward. If the variance of the differences between the models with common random numbers is greater than the sum of the variances, then in that case, maybe I should just use independent replications because I'm not picking up any benefit by coupling their inputs together. All right, so that's common random numbers in a nutshell. Any questions about that? Is that pretty clear? This is the types of tricks that we're doing to reduce the variance in our simulations without losing any sort of connection to the real world. We just kind of use our ability to play with the random numbers to force the inputs to be the same, to kind of make for, it's almost like the perfect, that you couldn't do this in the real world. You couldn't go into the real world and say, I've got manufacturing line 1, manufacturing line 2, I'm gonna run exactly the same challenges down these same real manufacturing lines, but we can in simulation. Okay. Questions online? All right, so the other method that I wanted to talk about last time is that this one really applies to the real world as well, but this is known as control variates. And so this method here is a slightly different motivation here. So the idea here is, let's say I'm running a single simulation, and I know a particular variable like temperature or something like that, and I know it varies and it's going to affect the performance of this system. And I am measuring the output y, so I'm measuring the output of this system. And I know that this variable that I'm familiar of, like temperature, is correlated with this output y. And so you might imagine that if I'm measuring in a power plant, I might be measuring the power output. And I know that temperature is correlated to sunlight. And so if I know temperature data across a wide, across a whole year, then I can use the temperature data to sort of as a proxy for sunlight. And so if I know the temperature is going up, the sunlight's probably going up, which means the power generation is probably also going up. So if I'm running a simulation of this power system, and I'm interested in knowing how do different ways of running the power system affect power output, then I might want to sort of increase my statistical power on power output, and I can use the known information about temperature to do that. So let's get that a better idea. So I'm just kind of trying to summarize this here too. If my output is correlated with temperature, then my idea here is that I'm going to subtract from each day's temperature a special amount proportional to that day's difference from its average temperature. So in other words, if I know this is a particularly hot day, then I'm going to assume that it's going to be a particularly power output favorable day. And I'll be able to then subtract off the variance due to the temperature so that all that's remaining is the variance due to the change in my operation strategy. So that's the idea here. Is I've got a variance source due to temperature that applies to any strategy that I choose, but I'm interested in what is the variance due to the changing the strategy. So, whatever operational strategy, whatever parameters I'm trying to optimize inside the power plant, I want to know that the difference in performance I see from simulation 1 to simulation 2 is not due to a difference in temperature, it's due to a difference in this strategy. And so I'm going to use known information about how the temperature is varying to give me a better idea of how the performance is varying. And so let's see that a little bit more mathematically here. And so the idea here is, again, y is my output, x is some variable that I know of that is probably correlated with my output. And so you can think x is the average temperature of a day, y is the power output of a day. I know the average value of the temperature over all the days that I'm simulating. I know the temperature on each day. So on each day, I can measure the difference between that current day's temperature and the average temperature across all the days that I'm simulating. So what I'm going to do is I'm going to create a random variable. This will be our control variate that we'll talk about here, called z. And it's just going to be the performance measured on the output of my simulation minus some scaled version of this difference in the thing that it's correlated to. So X is my temperature, expected value of X is the average temperature, and I need to figure out the right scaling coefficient there, but this is just a scalar. It's just a number, a real number, C. And so this control variate, if I say, well, what's the average value of this random variable? Well, that average value of the random variable is just the average of the performance that I'm trying to measure anyway, minus this term here, which is just distributing the C through there. And if you look at that, well, this is all going to be canceled out. And so the average value of my control variate is the average value of my performance output. So this is an unbiased estimator of my performance output. So I'm doing this funny thing where I'm subtracting off data from my performance output. But if all I'm really caring about is estimating the mean performance for this strategy, then I might as well estimate the mean Z, because the mean Z should be the same as the mean Y. The trick is, can I choose a value of C that makes the variance in Z less than the variance in Y? And if I can do that, then I can estimate this average value, like standard error of the mean, with less variance so that I can use less replications. And so how do I do that? Well, how do I choose the C? Well, I'm going to put a little calculus in here. I can take the variance of this Z variable that I've created and do a little probability here. And I just plug in the Z right in there. And then I use a little bit of what I know about the variance of variables multiplied by constants and all that. And so just from basic probability theory, you can go from line 1 to line 2. And then now I've got this thing here that involves the covariance of X and Y, and it has this C. And I can just optimize this thing to minimize the variance in Z. So I can take the partial derivative of this thing with respect to C, set it equal to 0, and solve for the C star value that minimizes this variance. And if you go through that exercise, you'll find that the C star value that minimizes the variance is this thing here, which is the covariance, which is a measure of correlation between X and Y. So you can calculate covariance divided by the variance in X. And so this is how much X and Y relate to each other. And this is divided by how much variance was actually in the thing that I knew about, like temperature. So you can always do this. There's no penalty to doing this, because if these things don't vary with each other, then this will be just 0, and it just goes away, and Z is equal to Y. So this is always the strategy you can do in real data or in simulated data. You look at a long series of data from your 100 replications. You look at all the temperatures corresponding to those 100 days that you simulated, all the performance outputs that corresponded from those 100 days, and then you can calculate the variance, you can calculate the covariance, you can solve for this thing, and instead of operating on the Y column, you create a Z column that's written out this way using this C thing here, and that Z column will be an estimator of Y with less variance than Y itself. So that's what we do there. So, and so this is just me sort of saying here that the same thing I mentioned before, the more that these two things vary together, the more this will work. The less they do, the less it'll work, but there's never a penalty in doing it. And so, and in fact, you might have heard about this. So this is called control variates. If you've ever heard in a scientific study, they'll say, we wanted to estimate the effect of, the effect of Skittles on college performance or whatever like that. And somebody will say, well, isn't there they'll say, well, couldn't of these other things also affected the college performance other than Skittles, like income level or all these other sorts of things? And they say, well, we controlled for that. What they mean by controlled for that is they use a linear regression, which does this in the background. So when you hear someone saying, we controlled for all of these other variables that might confound our results, what they're saying is we looked at how much our response variable varied with the thing that you're talking about, and we subtracted out the effect that was due to that thing, so that everything that was left over was only due to the Skittles that we were studying to begin with here. That's the same thing that's happening here. We're saying that there is a lot of variance in the output. Some of that variance is explained by temperature and not by our change in strategy. So not by our choice to use a particular way we're adjusting the solar panels versus another way we're adjusting the solar panels. So we're subtracting out the component of the variance of performance that is just due to temperature, so that all that's left over is the component that is due to our operational strategy. And that allows us to better estimate the performance of one strategy versus another and compare them to each other and so on. So that's what we mean by control variates. So before I show kind of a numerical example, are there questions about this? What I mean by control variates or these formulas. That's a stretch, I think. Yeah, no problem. Questions online? Okay. So as an example of this, and this is a little bit of a contrived example, but it's compact so that I can show it on here without a complicated simulation. So you can imagine that, what if I have a random variable x, which is a uniformly distributed random variable between 0 and 1. It's a random number. Its mean is 0.5. Now, I would like to know, what if I take that random variable and I run it through the exponential function? It becomes a new random variable, but I don't know what its mean is. So I'm like, well, I say, well, if I take the exponential of a random number, what's the mean of the output? I'd like to know that. So you can pretend that this X is a simulation model. So this is the day's temperature, this is the day's power output. So I run 1,000 replications. So these are my 1,000 temperature variables. These are my 1,000 simulation runs. And I end up getting a mean and a standard error of the mean summarized here. So this is the mean, this is the standard error of the mean. Now, I do know mathematically for this model that this is the value, the precise value I should get for this. So, so this is pretty close. So it's not that far off from there, but is there a way we can reduce this variance without running any more replications? So what I'm gonna do is I'm gonna say, well, let's just estimate the variance of my X and the covariance matrix here, but the covariance of my X and Y, how they correlate with each other. So, and this is all done in MATLAB. You can do this, any stats package will allow you to run these things. And I get that the variance in X is 0.084, the covariance between X and Y is 0.1440. So I set a C value equal to the covariance divided by the variance, 1.686. And with that, I create a new variable called Z. So for every Y, I'm gonna subtract 1.686 times the corresponding X minus 0.5. So that's what I've got down here. So for every Y, I subtract 1.686 times the corresponding X minus its mean. And the mean of that resulting, the mean of Z is 1.72, and the standard error of that mean is 0.002. So this is a far smaller standard error of the mean. And this estimate here, if you think of this as an interval estimate with standard error, is much closer than to the 1.7183. So without doing any other replications, I was able to get a much better estimate of my performance variable, my Y output there. And you can, again, do this not just with simulation, any data set. If you manage to find a data set where you can correlate outputs to some other variable that you know about, like temperature over days or something like that, then you can subtract out the variance due to that other variable. And then what you're left with will be a lot less variance that you can then attribute to the things you actually care about. So those are control variates. Questions about control variates, CVs? Okay. All right, so those are the two VRTs that we start with. Now we get into a little bit more exotic VRTs, antithetic variates and importance sampling. And so let's just hop right into it. So we started out with common random numbers. This is a way for us to better estimate relative performance of two different models by reducing the variance. What if we wanted to estimate, better estimate absolute performance of a single model? Is there a common random numbers analog to that? Can we do some trickery with random number seeds that allows one model to have a much more precise estimate. And we can. So if we look at the outputs from one model, so this on the x-axis, these are replications, say come out of ARENA. So replication 1, 2, 3, and you've got your simulation output. Say this is average wait time or something like that. And so you see it's all over the place. Sometimes they're below average, sometimes they're above average. And we know by the kind of law of large numbers that if there's always going to be, if for every above average case, there'll eventually be a below average cases, eventually. And if you take enough samples, all of the really high above average cases will cancel out with all the really low below average cases. And that's how you end up getting a convergence on the mean. But we need lots of replications to do that. And so wouldn't it just be nice if the universe was forgiving and would just give us an above average followed by a below average, and then another above average followed by a below average, and so on. Then we wouldn't necessarily have to wait for hundreds and hundreds of replications to get everything to cancel out so we could converge on the mean. So is there a way that we can engineer our simulation so that it is highly likely for us to kind of take all these red ones and move them, or to resort them so that we get, for every above average, a below average kind of right next to it, so that instead of needing 100 replications, maybe after 10, we'll have enough of a balancing effect that we'll be able to end up getting a good estimate of this mean. And that's what we do with antithetic variates. So the idea here is that we are going to play with the random number stream so that every odd replication, 1, 3, 5, and so on, uses a fresh draw from the random number generator, but every even replication is going to use a specially mutated version of the previous random number draw that helps guarantee that the next replication will be on the other side of the mean, so that you get this back and forth effect, so that you need less replications to estimate that mean. So how do we do that? Well, and this is going to depend upon kind of the math here is that what we're going to do is we're going to take the, for every 2 replications, an odd and an even, 1 and 2, 3 and 4, 4 and 5, we're going to take each one of these and average it together, and that will become a new replication, and that's the so-called antithetic variate. It is the average of every pair of replications. And so if I think about mathematically what that looks like, so A is my odd replication, B is my even replication, and this is their average. The mean of this antithetic variate is just the mean of the performance here. It's an unbiased estimator of the mean, just like we saw with control variates. The variance of this average of the odd one plus the even one, 1 plus 2, 3 plus 4, and so on, is going to be the variance of the odd one plus the variance of the even one plus their covariance. And so if we can somehow engineer the simulations so that there is a negative covariance, so in other words, if one is likely to, the first one's likely to be high, the second one will be likely to be low. If the first one's low, the second one will likely be high. Then we're guaranteeing that this variance here is going to have a lower variance than the variance of the thing that we actually want to estimate y. And so that's why this technique is going to depend upon a negative correlation. So remember, in common random numbers, we depended on creating a positive correlation between different models. Here, we're trying to create a negative correlation in the same model from every other replicate. So how do we do that? In the first, or every odd number replication, so in the first replication, we draw, we have a pseudorandom number generator seed comes in, and then we draw, however many random numbers we need for that replication. So every time you draw an exponential, it's actually drawing a random number, and then it's transforming it to an exponential. Every time you try a normal, it's drawing a random number and transforming it to a normal, as we learned how to do before the midterm. And so one replication might draw thousands of uniformly distributed random numbers. So the pseudo-random number generator seed goes in, replication 1 draws these 100 or so. For replication 2, what it's going to do, and so this is just showing you replication one here. So the pseudorandom number generator goes in, it draws, say, an exponential. The exponential goes into your simulation model logic. Your simulation model is this H function, and then you then get an output Y. So this is kind of what's happening through one replication. The random number seed goes in, generates tons of random numbers, generates tons of whatever random variates you actually want are, goes through your logic, gives you an output. All right, so for the second, so this is for run one, this is for replication one. For replication two, instead of drawing a new random number, instead of calling out and drawing new random numbers, we take every random number we drew in replication one and do 1 minus it. And that gives us a uniform distributed random number. But if we happen to draw 0.1 here, it gives us like 0.9. If we drew 0.8 here, it'll draw us 0.2. So we get the kind of the flip, the other side of the uniform distribution for every even numbered replication. So again, for every odd number replications, we just draw random numbers from 0 to 1, and we use as many of them as we need. We remember all the ones we drew, and then for the second replication, we then just take the complement to them. So if we drew on one half, we then transform it to the other half. And then we go through the same simulation logic and we get a different output. Now the hope is that by drawing a number that, like, we know that a low number, like a low random number going into an exponential generator is going to give us, I think, if you think about it, a large exponential value. Whereas a high random number going into an exponential generator is going to give you a low exponential value. And so the hope is here that if we flip this, then you might have had like if you have a short inter-arrival time for customer one in replication one, customer one in replication two is going to have a long inter-arrival time. So it's going to totally change the nature of these things, hopefully in a consistent way, where if it was easy for replication one, it'll be hard for replication two, and so on. So that's what we're trying to generate here. And so after we do all of that, we're going to get an output for replication one, an output for replication two, which did not use a new draw. It used this thing that depended on the draws from replication one. We take the average of that, and that is our antithetic variance, the average of those two together. And the variance in the output should hopefully be reduced. And so we still, if we want our number of antithetic variates, we still need our number of pseudorandom number seeds. But the correlated replications, so the other R, so we need R odd replications, but the even replications don't pay the random number generator cost because it's just 1 minus these random numbers here. And so what that ends up looking like, so here's a book example you've got here. These are independent replications where we've got two models, one filled, the other one open. And then what they did is they generated a kind of an average of each one of so every, replication one, replication two, and their average will be the dark bar in between them. And this is showing you that when you don't have antithetic variates turned on, when you just average pairs, you get this kind of ugliness here. But when you flip on the antithetic variates, then this bar has far less variance here. So it's kind of tightened down around the mean here. And that's because there's sort of a consistency across these replications, so that replication one and replication two tend to be on the opposite side of the bar. So you don't get, there's these cases up here where both replication one or replication whatever, replication even and replication odd, up here, they're both above the average. Over here, it tends to be the case that all the replications straddle the average. So when you average two adjacent replications, they tend to be even closer to the average. That's what's going on with the antithetic variates. Okay, so are there, before I do a little numerical MATLAB example of that, are there questions about that? To kind of clear what I mean, the big thing is understanding what's going on here. I'm trying to see here that, because and I'll tell you, like on final exams, in order to we'll say like, and you can see examples of these that I put online from past finals. Sometimes I like to combine these, like make sure everybody remembers how to do their inverse transform sampling. So what I'll do is I'll say, do an inverse transform sampling problem. So, generate an exponential or something like that. But then instead of asking you to tell me the exponential that you generate, I'll say, but use antithetic variates and generate the first antithetic variate, which means that I want you to take the random number I gave you, plug it into your inverse transform sampler, and then also know to do 1 minus that random number, plug that into your inverse transform sampler, take those two outputs and average them together, and their average is the answer that I'm looking for. So it's that I want you to sort of know the behind the scenes, what's going on when you do antithetic variates. It's doing this 1 minus thing. So is that clear? Questions online as well? All right, so let's see an example. Again, this is a contrived example, just that I can put it nicely on one slide using all MATLAB here. So it's another kind of Monte Carlo example here where, again, I've got some X variable, which is my random number, and I'm trying to then estimate this performance variable of this Y that's coming out here. And so what I'm gonna do, so this is exactly the same as what I did before for control variates. So we know what the expectation is here. So I'm gonna do 1,000 replications of independent replications, and I've got a certain mean and standard deviation or standard error of the mean, same thing as we had before. Now to generate my antithetic variates, what I'm gonna do is an alternative way of this, is I'm gonna generate 500 replications, 500 random numbers, and then instead of 1,000. So here I did 1,000 random numbers and just did the experiment with all 1,000. Here I'm only gonna generate 500 random numbers, and then the other 500 are going to be 1 minus the original 500. And then I'm going to then pair up those so that for every random number in XA, it gets paired up with the 1 minus version of it. And I'm gonna take the average of the simulation outputs for each of those. So if you think of exp, exp is, it's the exponential function, but you can think of this as your simulation. So your simulation, I run it on the random number from XA, and then I run it on the random number from XB. I get a performance output out, and I take the average of those, and that ends up being the Y for this one here, which maybe I should have labeled that Z in this example. And now, if I take the mean and standard error of the mean, then I find that I get a much tighter standard error of the mean, and this interval here, you're going to go this plus or minus this standard error of the mean is much closer to the expected 1.7183. So technically, I only ran 500 replications. I only drew 500 random numbers, so I drew half the random numbers. I still had to run my model over 1,000 iterations here, but if it's costly to draw the random numbers, this actually saved me in that, assuming that my model is actually relatively easy to run. And regardless of that, it's probably no more computational time than this one here. And I got a much tighter variance out. So with 1,000 replications, I did much better. So that's what went on with my antithetic variates here. You can do antithetic variates in the same way that you do common random numbers. You go into arena, you go into the seeds element, you can go through, and instead of selecting common under initialize option, you select antithetic. And what antithetic will do is it will ensure that every odd replication is followed by a replication that uses the negatively correlated random numbers from the previous replication. So it just does this, this back and forth for us, so we don't have to do it. So every odd replication will draw fresh random numbers. Every even replication will take all of the random numbers drawn in the previous one and do 1 minus them in order to generate that. And then you could get your outputs out of that, and you can then analyze those. I think, if I remember correctly, the output analyzer has an antithetic, has a couple of options for splitting out these, because you're going to have like this interleaving So you're gonna need to know that, like, well, I need to create these variates, or I need to create tie 1 to 2 and create an average, or you can dump these out into an Excel or a MATLAB or an R or a JUMP or whatever, and then you can average up these, every odd with every even, and generate that, and then do the analysis on that. And then, like, this is just echoing that if you used an interrival stream other than 10, you can put that in to the expo as the second argument. And then you say the outputs for your replications, you create these averages, and then you can do your analysis, one sample analysis. So questions about antithetic variates, or AVs as we call them. It's kind of like common random numbers, but for absolute performance instead of relative performance. Questions online? Okay. All right. Okay, so let's, for kicks, let's do an attendance question here. And the question I'll ask is, what type of correlation, positive or negative, do we need for antithetic, I'll say, do we need between adjacent replications for AVs to work? So do you want to induce a positive correlation or a negative correlation between adjacent replications for antithetic variates to do their magic? All right. So, and while we're sitting here, I will mention that antithetic variates, like common random numbers, don't always work. It's another one of those cases where you really should run a pilot example or pilot study, and you could test whether you get a decrease in variance or not. I think I probably had a slide on that I just probably blew through here. Looks like I didn't. Well, but it's a similar case for because antithetic variates, if we go back to the mechanism, like showing why they work here, if you happen to have the wrong covariance here, then the variance in this average is actually going to not be an improvement over the variance in the standard performance variable. So you really need the right type of correlation in order for these to work. And so you typically have to run a type of a kind of a pilot study to make sure that you're actually doing better with the antithetic variates, similar to the common random numbers. All right, so the last VRT that we want you to see in 475 is importance sampling. And so this is another way to do, this is something that you really only can do in simulation. There's really no analog in the real world. Kind of like antithetic variates, but this is even weirder. But importance sampling it's used in a wide range of applications where you're using Monte Carlo type analysis, stochastic simulations, to estimate rare events. And so like, imagine if you want to estimate how often a catastrophic but extremely rare event, like a nuclear reactor reaching a certain critical temperature. So I really am trying to estimate what's the probability that a reactor temperature or a simulated reactor temperature is greater than some threshold. If it gets over that threshold, it's meltdown. I really need to know how often this occurs with the operational strategy that I've set up for this nuclear reactor. And so, so how do we run this? So imagine we want to simulate this. So what we're going to do is what we'll call sim our simulator of the nuclear reactor. So I'm not going to show a simulation of what a nuclear reactor looks like. We'll just bundle it all in a black box called sim. And then I imagine that my nuclear reactor takes input, so my input model from a random variable X that has a certain PDF. So this is our input model that has to do with some stochastic input that we've used in the simulation of the reactor. So we want to use our simulation replications to estimate this probability. And we're going to do that by saying, well, the estimate of this probability that our simulated temperature is greater than the threshold, we can estimate that by saying, what's the, we're gonna take these, this bracket here, this is called an Iverson bracket. It basically returns 0 if the thing inside it is false, and 1 if the thing inside it is true. And so we're basically saying, how often is the simulation greater than the critical temperature? If it is, it'll be a 1. If it isn't, it'll be a 0. If we take the average value of all the 0s and 1s that come out of this, how frequently does this condition occur? Then we get an average that looks like this. So it'll just be for our finite number of replications, we're just going to count how many were greater than the temperature, divide them by the temperature, and the result will be a number between 0 and 1, which you can think of as how frequently this thing came up as 1, and that will be an estimate of this probability that this occurs. All right, so that's how we're going to estimate this probability. We're going to run a bunch of simulated nuclear reactors and see how many of them melt down. Now, I have to get in a little bit of the math here, just so we can see how this importance sampling works. This expectation, so if you go back to how we defined expectation earlier in the class, or if you go back to 380 and 385, then the definition of the expectation of a random variable x, well, it's the expectation of our simulation model over the distribution x, where that's our input model, is this integral. So I'm integrating over all of the values in my input model, where I'm taking the particular simulation at that value of the input model times the probability of that model from the input model. So this probability density, I'm sort of saying, if I go up here, I'll just use the mouse here, tau here is a dummy variable. For every value of my input model that's going into this, whatever the stochastic model is, temperature or something like that, for every value of that, it has a certain probability density, and that probability density scales the output I would get if I forced that value to actually be that one in the simulation. And then I take all of those and I integrate them over all of the possible values of the input, and that's what an expectation is. And so that's how we get an expectation out. So with importance sampling, I'm going to do a little bit of some modifications of this that don't actually change the output, but allow me to focus on some different elements that will allow me to kind of toy with the input to allow me to get a better output out with fewer variants. And so what I'm going to do here is I'm going to create a new random variable y, and this will be, you can think of it as a new input model. So X was the old input model, the interarrival times going into if you don't like the nuclear example, think of X as like an interarrival distribution going into an airport. And Y is going to be a pathological interarrival time going to an airport where like everybody arrives right on top of each other and the airport is just constantly getting bursty traffic. And so I'm going to create this new variable Y with its own PDF where the support of it matches the original input model. And so if the original input model was defined from 0 to infinity, the fake input model is also defined from 0 to infinity. Now the expected value here that I'm trying to estimate of my simulation is just going to be the integral with so all the front half here is the same. But what I'm going to do is I am going to just sort of add in this, I'm not changing anything here, but I'm just multiplying my f of x here by f of y over f of y. And so what that does here, it doesn't change, this is identical to the form right above it. But by doing that, it introduces this funny little scalar here, which I'm going to call a likelihood ratio of the PDFs f and y. So this w of y is just f of x divided by f of y. It's the actual input model divided by the fake input model. And then that thing gets scaled by the probability density function of the fake input model. So this expectation is over the fake input model. So what I'm trying to get at here is, what I'm saying is, what this tells us, what this math tells us here, is that we can either simulate with the real input model where everything's sunny in Philadelphia all the time. Or we can generate a fake input model that is going to generate a lot of catastrophic events. So we can make it so that we're just going to put a stress test on this nuclear reactor. And that will generate a lot more failures in the nuclear reactor. And so we will now get an appreciable number of failures. We can take those failures and we can scale them by this likelihood ratio. And then we can end up saying, well, given in my bizarro world where you got meltdowns every day, what does that mean about the real world? Well, if I know the difference between these two input models, the real world and the bizarro world, I can kind of scale back the bizarro outcome into the real outcome. So I can dial up. So basically what we're saying is the signal to noise ratio of nuclear meltdowns is low. So I'm going to imagine I went into a universe where there's meltdowns all the time. And from that universe, I'm going to say how many meltdowns are there in that universe. Given I know how weird that universe is, I can rescale those meltdowns to figure out how many meltdowns there would be here. And that will allow me to run 10 replications in Bizarro universe instead of 1,000,000 replications here. And that's what we do here. And so that's what I'm saying that here is that this is going to, this likelihood ratio here. So all of this math, you can throw it away and the ending result is down here. And this is what we're going to be, this will be the importance sampling. So down here, what we've got is that if I run my R replications using a Bizarro input model that is going to induce these rare conditions to happen less rare, I mean, more often, I can then take the simulation outputs, whatever they are, under this weird Bizarro case, scale them by the likelihood ratio, which is just the ratio of the real input model to the fake input model. And after that scaling, take that average, and this will be an average in our universe, but it'll require fewer replications to get the same precision. And so we're purposely biasing our inputs to overemphasize conditions that are rare in reality. All right, so let's see like an example of that. So here I want to say I've got some simulation that I want to, again, my nuclear reactor example, how often is the nuclear reactor greater than 5? You could also say, how often do I get wait times on a call center that are greater than 5 hours? Well, hopefully that's super rare, but it's still a useful number to know. And so if my input let's say my input here is normally distributed as standard normal, then what I'm trying to say here is that if I take, so my simulation here is after a 1,000,000 replications from my simulation, where my input model is from the standard normal. If I take the mean, for example, of this, so this is what I'm trying to kind of say up here, is that how often are we 5 standard deviations away? That's basically what I'm saying here. And we know that if I take the mean of a normal random number, I'm going to take 1,000,000 normal random numbers and see how often are they greater than 5. Very often, this experiment will come out to be exactly 0. All right, so just to say this again, if I'm trying to estimate some calculation of, well, let's say I'm trying to estimate how often a normal random number is more than 5 standard deviations away. If I'm trying to do that, then I run 1,000,000 replications of a standard normal, and I come up with, of those 1,000,000 numbers, I get exactly 0. And I know I've kind of been babbling through this, but this part here, if I have 1,000,000 draws of a standard normal, why would the mean of those 1,000,000 numbers be exactly 0? How could that happen? It's a standard normal. So in the numbers I'm drawing here, the 1,000,000 standard normals, I compare them to 5, and they come up with either a 0 or a 1. A 1 if they're above 5, a 0 if they're below 5. And I take the average of that string of 0s and 1s. Why would I get exactly 0? Like why wouldn't we, like, it sort of should be surprising. It's not 0.0005 or something like that. So I mean, what does that mean about all of these numbers? if you go into MATLAB and you say, I'm gonna take the average of a million numbers that are either 0 or 1, and MATLAB spits out 0 as the average, what does that tell me about my million numbers? Yeah, they're all 0. That's what I'm looking for. They're all 0. So what we're saying here is this is so rare. It is so rare for a standard normal to be 5 standard deviations away that if I take a draw of a million of them, many of the times I do this experiment, I'm going to get exactly 0 out. So I am not going to properly estimate this probability. And that's what I'm trying to say here, is that the probability is super low, but I run a million replications, and what I find is that I get all 0 out. So I would have to run 10 million replications or 100 million replications in order to properly get this estimate. So what I'm going to do instead is I'm going to say, well, what if my input variable is not a standard normal? What if my input variable is a normal with variance 1 that's centered around 5? So arbitrarily, I know in reality, this input model should be a standard normal. I know that in reality, this parameter, it's stochastically modeled, but it should be centered at 0 with a standard deviation of 1. It should be a standard normal. But I'm going to throw that out, and I'm going to say, well, just what if I'm in some bizarro world where this parameter is centered at 5 with a standard deviation of 1. And so I'm going to throw that into my simulation model. Now, I need to calculate this likelihood ratio first. And all I do is I say, well, I need to do the PDF of the original value, or the true input model divided by the PDF of the bizarro input model. And that's just the PDF of a standard normal with the PDF divided by the PDF of a shifted standard normal. You can write out the expressions for those, do a little simplification, and there is your likelihood ratio. So this is telling me that if I rerun my simulation using this as an input model instead of that, yeah, I'm sorry. Well, so all of this, all right, so this I think was probably me. So going from here to here, these should all have been Y's. So that X should have been a Y, that X should have been a Y. I think copied and pasted and got it. So I apologize about that. Yeah, Y and Y there. So I got this likelihood ratio. What this is going to tell me is I'm going to run my simulation. So I'm going to take a million samples from not a standard normal, but a normal that has a mean of 5 with a standard deviation of 1. And I'll take those and ask how many of those are greater than 5. Lots of them are going to be greater than 5. And then I'm going to scale them by this likelihood ratio and then take the average value of the result. So let's see what that looks like. So in MATLAB, I drew, in this case, only 1,000, not even a million, 1,000 random numbers. Then this plus 5, it means that they're random. These are going to be, because a normal distribution is location scale, if I draw a standard normal and add 5 to it, it just becomes a normal distribution with standard deviation 1 centered at 5. So that's what Y is. This is the bizarro one. And then I'm going to say, how often are they greater than 5? I'm going to scale that by my likelihood ratio. So for every value of Y, it gets plugged into the likelihood ratio, which will scale this up or down as appropriate. And then I'm going to take the average of this scaled version. And that average is a really tiny number. And that really tiny number has a certain standard error of the mean, which is right here. And heck, it even has a confidence interval. So I use a confidence interval there. And this 95% confidence interval, or half width, allows me to calculate the 95% confidence interval down here. And you can see super tiny number, and the number we're looking at is smack dab in the middle of that. With only 1,000 replications, a million replications back here, and I was just getting zeros everywhere. So I would need to run, millions and millions of more replications in order to hope that the average would ever come close to this. But by modifying my input model to force the pathological condition, and then rescaling the outputs by an amount that relates to how I modify the input models, then I am able to get, with only 1,000 replications, a super tight estimate of the super rare event. And that's what's called importance sampling. So we're sampling from our input models in a biased way so that we get a greater number of the important outputs that we care about. It really only applies to these Monte Carlo type cases here, like we explored back whenever that was lab 3. You might find some cases when you're working in a discrete event system simulation like ARENA where you could do something like this, but you're going to hear that in that term importance sampling, it comes up in machine learning and other things like that, and it's this basic idea that whenever you're trying to figure out the frequency of rare events, you can manipulate input models in stochastic simulation so that you can make the rare events less rare, and then after you've calculated their frequency in the bizarro world, translate the frequency back into our world, and that's importance sampling. So questions about that? Importance sampling, or any of those other topics. So those were our 4 VRTs that I want you guys to know for this class, but also for the final. Common random numbers, which again are a way to introduce positive correlations to improve relative sampling. Control variates, which is a way of taking relationships between outputs and known inputs to subtract off variance so that you have less output variance to explain in your simulation model. Antithetic variates, which introduce a negative correlation in between replications to do absolute performance estimates. And importance sampling, which are a method typically employed in Monte Carlo sampling to make it you able to estimate the frequency of super rare events without having to use millions and millions of replications. And they do that by biasing the input models so that the input models create the conditions, the likely conditions for these bad cases, and then you can then translate the outputs back. So somehow in a universe where there's more signal to noise, you need fewer replications, and then once you estimate the frequency in that universe, you translate them back to our universe, and you get a really tiny number, even though you used a very small number of replications. So those are our 4 VRTs. So any questions about those? Will any of you guys use the VRTs in your final projects? Probably not. The common random numbers, you'll probably, some of you might use, some of you might inadvertently use because of the way some of your models will work out. The rest of these, I mean, you could consider using things like antithetic variates, but things like AVs don't become really important to use until you get complicated models that take forever to run. And if your models are, you can run 1,000 replications within 30 seconds or something like that, you probably aren't going to need to worry about these things. But when it takes you 10 minutes to run one replication, then any amount of replications you can shave off with things like AVs or CRNs is really welcome. So, so yeah, that's so that's kind of looking forward. It's more of these things I want you to know about. I don't anticipate you using them in your final project, except for maybe CRNs. All right, so with that, let's, I'll just put one other attendance question here. And this question is, what topic from the course do you feel you need the most work on? So tell me what you think you recall from the course is the murkiest. It's always useful for me to then scan through those and see how folks are doing. And otherwise, that's all I've got. Like I said, that's the last technical content. The next lecture will just be the final exam lecture. Come with your questions, complete that, that lockdown browser compliance test to unlock the final exam module, test exams. Feel free to send me some notes. You know, of course, the schedule will be, for me, will be a little bit haphazard over the holiday weekend, as I'm sure you guys will be too, but I'll do my best. And that's all I've got for you. So if you have any other questions, feel free to come up. Otherwise, I'll see you next week and have a happy holiday. Any questions online? while you're still hanging around here? If not, that's all I've got for you. I hope all of you have a good holiday. Okay, I guess everybody's hanging out.